Hi, this is John Isles and welcome to Geometer's Paradise. Today we're looking at Lesson 3 of Unit 5, proving the parallel transversal theorems. We have three objectives today. The first is that you should be able to write the parallel transversal theorem proofs. You should be able to prove the perpendicular transversal theorem, and you will be able to prove the triangle angle sum theorem, which is actually a theorem from next chapter, but our first opportunity to prove it is in this chapter. Alright, so here we go. Let's have a look at some of these theorems. And I need to take a quick picture of this. There we go. Alright, first of all, a reminder. The corresponding angles are congruent. Alright, alternate interior angles are congruent. Alternate exterior angles are congruent. And consecutive interior angles are supplementary. That's an N, I swear it. Alright, so these are the base rules for each of them, and the theorems themselves are on this page, complete with handy abbreviations. So the CAT theorem, corresponding angles, the I8 theorem, alternate interior angles, the I8 theorem, alternate exterior angles, and the CHAT theorem, consecutive interior angles. Each of these plays a big role, and this one is the one we're going to take as a postulate, and we'll talk about why that is here in just a minute. Okay, so let's go ahead and begin with the corresponding angles theorem. Now, we're going to segue here for just a second. I got to step out, and we're going to look at GeoGebra, and the way that we want to talk about the corresponding angles theorem is to say that we have two lines and they have to be parallel. So here's two lines, line AB and C. So there's a new line here that's parallel to AB. What we want to do is draw a transversal that goes through those two lines. Okay, and then we want to measure some angles, okay, because we don't have any tools that we can use to say that anything's congruent to anything else unless and until we start building some angles. So what I'm going to do is, for the sake of clarity, I'm going to hide these points, and then you'll remember that we build congruence by building circles that are the same size. So here's a circle around D, and then I'm going to use a compass to build a circle around E that's the same size. We're going to intersect the circle where it meets the lines. So now I'm going to be able to measure these two angles, and we check to see the angles are congruent using a compass. So I'm going to go from G to F, and I'm going to put that circle on I. You see how it goes through H? That's an indicator that this angle is the same size as this angle. And likewise, I can come over here. Nope, that's not what I wanted to do. I can come down here and go H to I, and then drop it on F, and it hits again. Alright, so this pretty much proves that corresponding angles are congruent to one another. We can measure all the rest of them very easily by intersecting the sides and then checking, and it's all going to come out the same. All four of the corresponding angle sets are going to be congruent to one another. Alright, so this is why we take one of them as a postulate. We can prove it by construction. So we would say essentially that, here we are, gotta hop back into the slideshow. Alright, so we would say then that angle 1 is congruent to angle 5 by construction. This is the only one where this is an acceptable build. Alright? All the rest of them you have to do otherwise, but you have to prove it. But this one, the corresponding angles theorem, we actually take as a postulate, which means it is assumed true, although we've shown it true using a construction. Technically, you would also need to show 2 and 6 congruent, 4 and 8 congruent, and 3 and 7 congruent. But we'll leave that for an exercise for the student later. Alright, so let's get into the actual proofs. So the idea here, when we do geometry, is that you want to assume as little as possible. So we don't build alternate interior angles by construction, because once we have corresponding angles, we're going to be able to build alternate interior angles by proof instead of by construction. And here's what we do. We grab an angle that corresponds to either 3 or 6. For example, angle 2, let me do that again. Angle 2 corresponds to angle 6. This is a corresponding angle relationship. And it's vertical to angle 3. So 2 is vertical to 3 and it's corresponding to 6. This allows us to build a chain from 3 to 6 using the corresponding angles theorem. So we say angle 3 is congruent to angle 2 because these are vertical angles. Feel free to use the abbreviation VAT when you write this proof. Okay, and then we say that angle 2 is congruent to angle 6 because they're corresponding. This is the corresponding angles theorem, or the CAT theorem. We have corresponding angles here. We also have a spinning wheel of doom. Oh boy. Well, this is a first. There we go. Alright, and that now we have to connect the dots. Okay, so if you look here, angle 2 is used to connect them, so we say angle 3 is congruent to angle 6 by the transitive property. And all of our proofs, except for the consecutive interior angles theorem, use this same pattern. It's vertical, corresponding, transitive. Okay, vertical, corresponding, transitive. Over and over again. Alright, let's look at the alternate exterior angles. Look at this setup. Okay, we have 1 and 8, and we want to build a chain to connect 1 to 8. All we have to do is pick a corresponding angle to do that. So we could pick angle 4, which corresponds to 8, or angle 5, which corresponds to 1. For no particular reason, I am going to select angle 5, which is corresponding to 1 and vertical to 8. Okay, so now we come over here and we say angle 1 is congruent to angle 5 because they are corresponding angles, CAT, and then angle 5 is congruent to angle 8 because they are vertical angles, VAT. Again, this is corresponding, this is vertical. Alright, now we have a connection from 1 to 8. I totally wanted to make that a red line. You know what, I could just undo it. There we go. Okay, so a connection from the 5s. So this sets us up for a transitive. Angle 1 is congruent to angle 8 by the transitive property of equality. Alright. Next up is the consecutive interior angles theorem. We need to connect 4 to 6 using corresponding angles. All right. Now this is much more difficult, but because we got to go through the whole linear pairs ordeal. But here's how we do it. You need to select an angle that is both a linear pair and a corresponding angle. So it's got to be like a linear pair to 4 and corresponding to 6. For example, 2 and 4 are a linear pair and 2 corresponds to 6. Or 6 and 8 are a linear pair and 8 corresponds to 4. It doesn't matter which way you want to do it. We'll pick 2. So we have a linear pair from 4 to 2, and then we have corresponding angles from 2 to 6. So since 2 and 4 are a linear pair, we can say that angle 2 plus angle 4 is equal to 180. This is actually a theorem called the supplement theorem, but we're going to call it the linear pair theorem. So LPT, linear pair theorem. Okay, and then we say that angle 2 is congruent to angle 6. This is the corresponding angles theorem. Alright, now, whenever you're congruent, you're equal. And what this allows me to do is to build a connection here into the supplementary angles. So we're going to replace 6, or we're going to replace 2 with 6. So angle 6 plus angle 4 is equal to 180 by substitution. Alright, that's your consecutive interior angle theorem. There probably should be one more line, and that line would be angle 6 and angle 4 are supplementary. Okay, and this is by definition of supplementary angles. Forgive my shorthand. Not quite enough room over there. Alright, now we have two kind of derivative theorems. The first is called the perpendicular transversals theorem. And the idea is that we begin with A parallel to B and T perpendicular to A. So T and A are perpendicular. And that means that these 4 angles are all congruent angles. Okay? 1, 2, 3, and 4 are congruent angles, but more importantly, they're right angles. So let's take angle 2, and we're going to call angle 2 a right angle. We can actually call all of them a right angle, okay? But we know that A and B are parallel, which means these 2 angles are congruent because they correspond. Alright, now since this is a right angle and 2 and 6 are congruent, that makes 6 a right angle as well. I do not know why I'm being spinny wheeled here. There we go. So this is a right angle as well. Alright, and that's kind of the way the proof goes. So here we go. T is perpendicular to A. That means that angle 2 is a right angle. Alright, this is because we have perpendicular lines. Okay, and then we say that angle 2 is congruent to angle 6. This is by the corresponding angles theorem. Alright, and then we claim angle 6 is a right angle. Alright, and this is because all right angles are congruent. It's actually the converse of that statement. So if you're congruent to a right angle, you're a right angle, basically. 6 is congruent to a right angle. And then this, in turn, tells us that T is perpendicular to B, because now we have a right angle. That's what it means to be perpendicular. So this is because, by definition of perpendicular lines. Which is actually kind of cool, because now we've used perpendicular lines to undo it and create a right angle, and perpendicular lines to redo it and create perpendicular lines. So that's your definition there. Alright, last proof for today, and this is the awesome, oh, I love this one. This is a great proof. Okay, this is an important proof, an important idea for the entire next chapter. And it goes like this. We want to show that angle 1, angle 2, and angle 3 sum to 180 degrees. So what we do is we take any triangle and we draw a parallel line to one side. So this line is parallel to this one. Okay? So we have two parallel lines. Now, because they're parallel, we are going to be able to connect 4 to 1 and 5 to 3 by alternate interior angles. So these are both AIA relationships. Okay? All we have to do then, since we know 1 and 4 is congruent and 3 and 5 are congruent, all we really need to do is get these three angles equal to 180. And sure enough, this happens to be a straight angle. So we can say that angle 4 plus angle 2 plus angle 5 is equal to 180 degrees because they are a straight angle. This is also the angle addition postulate. Okay. Now, I know that angle 4 is congruent to angle 1 because of the alternate interior angles theorem. I know that angle 5 is congruent to angle 3. Again, because the alternate interior angles theorem. So by substitution, angle 1 plus angle 2 plus angle 3 is equal to 180. Oops, need another T. Wow, that's just bad right there. Let's try that again. You cannot get in a hurry with these pens. Alright, that's it. This theorem is awesome. You must know this one. I'm going to put this on your Unit 5 test, and I'm going to put it on your Unit 6 test, and I'm going to put it on your final exam. You need to know this theorem. It's important, and it's one of the best uses of the parallel transversal theorems that we have, other than like the parallelogram proofs, and we're going to look at a couple of those here in another day. So there we go. Your homework assignment is to do all those proofs again and write them until you know them. Alright? So good luck, and I will see you in class tomorrow.